Hello, and how's everyone doing? You have a worksheet on your Google Classroom that's called Stoichiometry with Density worksheet. And this is kind of a review of all the stoichiometry you've ever had to do, plus a little bit of gas law to go with it, a little bit of density. Seeing if you can remember how to do all of that work. So as we get started here, I hope everyone can see that well, can hear me. We're going to look at this equation, and again, when we look at this, we're going to be able to use the stoichiometry and all the conversion factors in order to go from one number and presume through it. Again, and if you notice the equation, it says assuming STP. So if it wasn't at STP, we would have to make it into STP in any reaction. So we're going to assume this one is an STP, and we're going to learn how to do this so we can, if we were doing it in industry or whatever, we'd have an idea of how they obtain the numbers they obtain when they want to talk about percent efficiency and percent yield. So the first one says, and we're going to do this as an example so you can continue on with the rest. The corrosion of iron is represented by the following. We have the density of iron, which is somewhat important later on in the problem. And it says, what volume of oxygen gas will be required to produce 16 grams of iron 3 oxide? Now, again, volume of oxygen gas, we have not really discussed that in previous work. One thing we need to remember is that at STP, 1 mole of a gas is equal to 22.4 liters. Always. It doesn't matter what type of gas it is, it's always 22.4 liters. So let's move my paper up a little bit and let's go through this. It says what volume of oxygen. So we don't know the oxygen, so this is our unknown, and our known is our iron 3 oxide. So they're giving us, letter A, 16.0 grams of iron 3 oxide. And again, notice the number of significant digits that are given in that problem. You know, we all love significant digits. So there's 1, 2, 3. The 0 does count because it's a 0 after a decimal after a number. So given that, let's look at this a little bit more. We have to change it to volume of oxygen. I have to draw a straight line using my ruler just because I'm that way type of a person. So I have my straight line drawn there. First thing I need to do is put the molar mass here. Again, remember molar mass, so I'm going to take 2 times the mass of iron plus 3 times the mass of oxygen. And I'm going to obtain 159.6882 grams of it. Again, if you want to stop and make sure that I did that math right, I know some of you like to check on that. This is 1 mole of it. Now we use our ratio within the equation, and I know that 2 moles of the iron 3 oxide require 3 moles of oxygen. And since it's an STP, we can immediately go from 1 mole of oxygen to 22.4 liters. Now I'm going to go through and I'm going to math this. Again, you can do a variety of ways. As you know, you can multiply the numerators and get an answer, and multiply the denominator and get an answer, and divide the two. You can put it in one fell swoop, or you can use like parentheses and brackets. So as I did this, I took 16 times 3 times 22.4, I divided it by 159.6882, divided by 2, and I got a number of 3.37 liters of oxygen. I put that there so you know what I'm talking about. LO2. Now that's not a chemical, that's liters of oxygen. Okay? So that's what tell me what the volume is. Again, these are not meant to be like brand new types of equations or types of problems, but more or less the ones that would get you thinking about how we can integrate all of them. As we continue on in this one, the next one is what mass of iron would be required to react with 10 liters of oxygen gas. I'm going to say that you probably have your worksheet out and about, and you can follow this. And again, please stop when you need to stop, of course, so you can follow along and make sure you know what you're doing. So for letter B, I'm starting with 10.0 liters of O2. And because I'm in liters of O2, and we're going to assume again it's at STP, which is very important because then I can use that number 22.4. 22.4 liters of O2 is 1 mole of O2. And since I'm in moles, I can go and I can use that relationship. If let's just go back here, and I want to go to iron. So I'm going. They talk about my oxygen is my known, and my unknown is my iron. So I'm going to go back to my problem, and I'm going to put the 3 moles of O2 here, and the 4 of iron. And I know 1 mole of iron is from the periodic table 55.845 grams of iron. Made my line a little bit long. And I'm going to math it. 10 times 4 times 55.845 divided by 22.4 divided by 3. And I end up with 33.2 grams. As you can see, that's how we would integrate volume with this. All right, that's one way to integrate the volume. As of this point, I'm going to do letter C only because as a review, so we can review those numbers that are so important in chemistry and gives us a little more background. We have the word molecules now. Molecules brings up a whole nother number in from our memory bank, and that's called 6.02 times 10 to the 23rd. So we will be using that within our stoichiometric calculation. I'm going to again start with 6.50 grams of iron. Because I'm in grams, the only thing I know about grams is the molar mass. So I'm going to use that concept in my next stoichiometric ratio from the periodic table. 55.845 grams of iron is 1 mole of iron. And now I can go straight to the balanced equation. Looking up at your equation, you can see that 4 moles of iron need 3 moles of oxygen. So there we are. And we know that 1 mole of oxygen contains 6.02 times 10 to the 23rd molecules. And as I math it, if you can bear with me, let's go through that a little bit more on our calculators here, how to do that. I'm going to take the 6.5. Oh, it'd help to turn it on, wouldn't it? I'm going to take the 6.5 times 3 times, let's go back to that, 6.02, and we're going to use a scientific notation, divided by the molar mass, divided by the mole into moles, and I get a wonderful answer. If you see that, it's 4.255170561 E22. Realistically, though, we cannot write that. We can only have 3 significant digits, so it's going to be 5.26, because this 5 is going to round that 5 up to a 6, and then I cannot forget to write down the 22. Some of you have started doing this. That's why a lot of people can type faster, so you don't have to worry about those superscripts and everything else, and that is totally acceptable. This is a different one because they're asking for a little bit more thought than what maybe you've done in these last two. These are pretty much rote by now for you. But if we go to letter D, It says, what volume of iron would be required to produce 6.43 grams, or 6.43 times 10 to the 24th molecules of iron 3 oxide if it was reacted with an excess oxygen gas? All right, I'm going to redo my paper here so we can get to the problem a little bit more. And this is where we have to go up to the very beginning of the problem. As we move up here, we have to remember that what our coefficients are to indicate the number of moles and what the density of iron is, and that's going to help us quite a bit. It says, what volume of iron? Volume. This is the kicker right here. I'm just going to write here, we're looking for volume. And volume is molar times, we look at milliliters, liters, but it can also be, because it's a solid, of centimeters cubed. Oh, I'm sorry, you can't read that. But these are different forms of volume, milliliters, liters, centimeters cubed, which correlates to a number in our directions on its density, grams per centimeters cubed. This is going to help us quite a bit. So it says, what volume of iron would be required to produce this? So the only number that we know is 6.43 times 10 to the 24th molecules of the iron 3 oxide. We have a lot, looks like it says that we have a lot of oxygen gas, so then we're going to continue on. Let me get my straight line here. Well, that wasn't very straight, was it? And I know that from previous work that 6.02 e to the 23rd is 1 mole. Avogadro's number is helping us right there. And then from that, I go to my balanced equation. Because this says moles of iron 3 oxide, I must put moles of iron 3 oxide down here, which happens to be 2 from our balanced equation. They're asking for iron, so I'm going to go to 4 moles of iron. And then we have 1 mole of iron is 55.845 grams, I believe. Because that's the only thing I know. I mean, I don't really want to go back to molecules again, because that's not really going to help me very much. So I'm going to use that. Now I'm going to use that little bit of information they gave to me in the beginning of the directions. They say iron has a density of 7.86 grams per centimeters cubed. So let's look at that a little bit. And we have 6 grams per 1 centimeter cubed. Well, in a ratio, if I'm looking at ratios I can use in stoichiometry, I can basically go 1 centimeter cubed is 7.86 grams. Because I have grams up here. And I want to have, I have to match, I have to cancel that label off. So I'm going to use 7.86 grams of iron. Here is 1 centimeter cubed. Now with that information I can math it, multiply the numbers out. Remember to put in using your e, your exponent or your exponential, times 10 to the 23rd, and I can math it, and you can check me out later on your math, but it ends up being 152 centimeters cubed. That's your volume right there. So that's what enables us to find that value. Now when you find this value again, I'm looking at 3 significant digits because it's 1, 2, 3. I hope this helps in solving the rest of the problems. It looks like a lot of them you do not need to resort and try to find them what they are at STP. It says assume STP, assume STP. So you can go that way. You don't have to translate them into STP. I hope this assists you in determining how to solve problems on this sheet. We will try to get together soon and answer any questions you may have. Have a great day.